So this is my first time in Cargèse and I feel very fortunate to be here. It's a place which is full of history because it's been a place where particle physics and physics have been discussed with students for decades now, and it's a very beautiful setting. There's something really wonderful about doing physics in a setting with the sea roaring behind you and away from the laboratory, away from the lecture theatre. Just talking about the key elements with the students is really a remarkable experience. The other great thing is that this year there are 4 lecturers and about 30 students, which really means that they get a lot of contact time. We have a lot of time to discuss with them at the coffee breaks, and they come up with wonderful questions, and it's kind of a pleasure sometimes to be challenged as well in our own beliefs.
Here in Cargèse, it's been a different approach to pedagogy, for instance, like learning in a different place, in different environment. The discussions, for instance, we have been having here is not like the typical class type we have been experiencing so far, and I think it's been very great.
It's a beautiful place. We are having very good treatment. Better than I expected, so I think it's good.
We have different professors having seminars and talking on various topics, and oftentimes things that we probably could not have seen in the classes.
The lecture I gave was about unusual signatures in the Standard Model and how we look for them in the ATLAS and CMS experiments.
I'm here to talk to you about Feebly interacting particles, and I've permitted myself to expand the brief a little bit to talk about other unusual signatures. Now, probably all of this means nothing to you right now, but my objective over the next 2 times 1.5 hours is to present to you a different view of how to look for new particles at the Large Hadron Collider.
The general idea is that we look for lots of different types of new physics, which could be beyond the Standard Model of particle physics, which we know and love. But some of them could be different from what we imagined when we designed ATLAS and CMS.
I'll try to keep it didactic, but what I'm showing you is cutting-edge research, right? It's some of the stuff I'm going to show you is going to be presented tomorrow at Montréal. Okay, so some of the stuff is quite old, and some of the stuff is general motivation, but generally speaking, I'm not going to hold back. So, okay, I make this responsibility to you, but then you guys have a responsibility to me.
So the idea is to say, let's check our blind spots. What kind of blind spots do we have? And we've identified a few of them, such as particles with long lifetimes, which would be thrown away as, let's say, instrumental noise. But we now know that these could be a well-motivated source of new physics. So the lecture was about looking for these kinds of new signatures in ATLAS and CMS.
I like the lecture we had this morning about the long-lasting particles and the feebly interacting particles, that sort of stuff. was cool.
In fact, he was presenting results that were presented like yesterday. So this is like new information that you could probably not get anywhere else. So that was really nice. And the way he presented it was very engaging.
I enjoyed a lot the lecture on the long-lived particle because these particles are the blind spots of the LHC, and it's a proof on how, if you would like to go on with the modern and more powerful colliders or accelerators, you should be sure to not leave some new discoveries while attending to go on and to discover more and more.
So today I did a presentation here in Cargèse, and it was simply about my bachelor work. So my bachelor presentation I did in Bologna when I graduated, and it was like very much related to what we're doing now, since it was a measure of a very important parameter, the gamma parameter of the CKM matrix, so very particle physics. And it was very nice. It wasn't planned at the beginning. I had the presentation in Italian, but it worked out anyway. And because we know, like, physics is a universal language. Yeah, it was very fun and also very interesting to revise my presentation, because at that time, of course, I had less physics background, less particle physics background. So now, like, re-looking at the presentation, I actually understood more stuff that previously I couldn't understand, and now everything, like, makes actually more sense. School here in Cargèse is amazing. It's like an amazing place. It's very good. I woke up this morning and I opened the window and there was like waves splashing into the rocks. It was very nice to wake up with that view. Then also the lecture time is, I think it's scheduled well, and with the breaks and stuff, there is like a vibe, a friendly vibe here. It's not professional, but you get to know also professors and stuff. You get more close to them. There is like a friendly vibe all over the institute.
I presented my bachelor thesis with Professor Jean that is on the path integral formalism in quantum mechanics. So basically it's a new way of computing things where we take all the possible paths a particle can take all at once, and it's a really beautiful new formalism that helps to understand the quantum fluctuations. The school in Cargèse is really cool because here the weather is not what it was supposed to be, but it's a nice setting to study physics, and we are here with our friends.
Corpe has introduced the students with a practical work in which an hypothetical particle could have been found in some data. And so students were chasing after this particle during the week.
The idea is, in 20 years in the future, someone proposes a new model that involves a new particle that can decay to 2 photons. And I asked them to be in the situation of being particle physicists in some experiment with access to data that could either prove or disprove this theory.
Trying to figure out the mysteries of the universe at whatever collider is operating at the time, maybe at the end of the high-dimensional CHC era.
And what I asked them to do, therefore, is to take some training data sets of what the signal would look like in different hypotheses in the background and use Python to design a search for these particles basically from scratch by themselves.
And a colleague of yours, who you met during your IMAPP, became a theorist during this time and has just come up with a brilliant theory that explains the hierarchy problem and the, the dark matter, everything, but all she has to do is add 1 boson. It's amazing. Don't ask me how she did it. I don't know. I'm not the theorist, okay?
Now, the fun of this exercise was that I gave them, at the end of the programming challenge, real data set which either contains the new particle or not. And I didn't tell them whether it was there or not. So it was for them to design their analysis and tell me, yes, the new particle existed, or no, the new particle didn't exist. And if it did exist, then with what mass and what cross-section, so what probability of being produced. So it was really up to them to simulate the experience of discovering a new particle, just like we did in 2012 with the Higgs boson. The question is probably, well, did it exist or not? And the answer is it depended on the student. I gave them each a different data set to practice with. And at the end, I also gave them a list of alternative data sets with 10 hypotheses, 10 different universes, and asked them to tell me in each one, yes, no, did it exist, and with what mass. And the best solution won a fabulous prize that I was able to give them at the end of the week. I was really impressed with the contributions from the students. Instead of just doing the simplest possible analysis, some of them went really far, implemented machine learning techniques, anomaly detection, and things that I had never thought to try for this exercise, which I had designed to be relatively simple. So I was really pleased with the contributions from the students, and indeed, most of them identified correctly if it was there or not.
I'm liking a lot of to search the new bosons.
Because we are actually instrumenting things and we are actually trying to solve the things by ourselves.
The challenges he gave to the student for the search for X boson is very, very interesting. And I so much like the challenge among the students.
It was a really good one.